Section 10.4 is comparison test. This is similar to what we did in section 8.8 with the direct comparison test for infinite integrals. So we can determine the convergence of a geometric series, a p-series, and a telescoping series, and others now using like the p-series and the nth term test for divergence. It's possible to test the convergence of even more series by comparing their terms to those of a series whose convergence is known. We know how to determine the convergence of quite a few different series now, don't we? We can use geometric series, telescoping series. We could use the integral test to determine convergence and the nth term test for divergence. So we have a variety of tools in our toolbox now. The thing about the direct comparison test is that you have to know the convergence or divergence of the series that you're comparing to. So here we're going to let the sum a sub n, c sub n, and d sub n be series with non-negative terms. Suppose that for some integer n, we're going to say d sub n is less than or equal to a sub n is less than or equal to c sub n. The c here stands for converge. The d stands for diverges. If the series that we're wanting to know about is less than a series that converges, then our series will also converge. That's what this part A means. If the series that we want to know about is bigger than a series that diverges, then our series diverges. The reason a series would diverge is because the terms of the series don't get small enough fast enough. If a series converges, then the terms of the series get small enough fast enough. We have this relationship between the terms of the series, or between the sums of the series. A sub n is going to be less than c sub n is going to be greater than d sub n. So this doesn't have to be true here close to the beginning of the series, like at n equals 1, 2, or 3, but it has to be true for some n greater than or equal to some point. So this point at which this relationship starts, I'm going to call this capital N, this point where the relationship holds. It doesn't matter what's going on before capital N, it matters what's happening past that for some value of n greater than this capital N. If the bigger series converges, that means that the terms of this series get small enough fast enough that our smaller series is also going to converge. If the smaller series diverges, what that means is here d sub n, these terms don't get small enough fast enough, so a series with terms that are bigger, they're not going to get small enough fast enough either. So if your series is less than a convergent series, the series you're comparing to is going to converge. If your series is bigger than a divergent series, your series is going to diverge. That's what this means right here. Now this isn't drawn so that we could say c sub n converges and d sub n diverges. This is just saying that if this is the relationship between your series and if this diverges, then your series diverges. If this converges, then your series converges. I just drew this picture to show you the relationship between these series at some value greater than capital N. This is the relationship that's going to happen because we said divergence trumps. And what causes a series to diverge is the numbers don't get small enough fast enough. In example 1, we're asked to use the comparison test to determine if the following series converges or diverges. What we need to do is find a series that we can compare this to. Typically what we're going to do is we're going to strip away the constants and just look at the variables, which is going to be the variable of the index of the series. So I want to compare this to k equals 2 to infinity. So we're going to compare this to the series k equals 2 to infinity of 1 over k squared. Because as we're going off to infinity, you're multiplying it infinity squared times 5. It's not going to really matter all that much in the long run. And if you add a constant to infinity, it's not going to matter that much in the long run. When you're trying to decide what series to compare your series to, just strip away the constants and look at the variables here. So we want to compare it to this. That means that I need to know something about this series. Does this series converge or diverge? This is a convergent p-series. If we look at our p-series, it says that the series where we have n equals 1 to infinity of 1 over n to a power is going to converge if that power is bigger than 1. The power right here is 2. That power is bigger than 1. So this is a convergent p-series. So then we need to look at the relationship between our series and the series we're comparing it to. So we're going to graph those two series. So this is the graph that I got whenever I graphed the function that we were given in blue and the function that we're comparing it to in red, and this is the window that I used. So looking at this, we can see that the series that we're comparing to, the 1 over k squared, is going to be greater than the series that I'm wanting to know about. Because I found a bigger series that converges, my conclusion is that our series converges by the direct comparison test. When you're using the direct comparison test, strip away the constants to see what series you're going to compare it to. Graph the two functions to make sure that the inequality holds once you determine that that series converges. And then your conclusion is that our series will converge by the direct comparison test. If this relationship doesn't hold, you may have to do some algebraic manipulation to things or find a different series. But you have to have some idea before you start the direct comparison test whether or not the series converges. And when you strip away the constants, that series that's left over is going to tell you or give you an idea of what you expect to happen. In example 2, we're asked to use the comparison test to determine if the following series converges or diverges. When I strip away the constants here, that 9 isn't going to matter. I'm going to compare this to the series k equals 3 to infinity of 1 over, and now I'm taking the square root of k squared. I'm not going to worry about that constant 8. And when I take the square root of k squared, I get k. And what does this series do? This is a divergent p-series because when we look at our series test for the p-series, we're told that the p-series diverges if p is less than or equal to 1. So we know this is a divergent p-series. Then I need to look at the graph and see what the relationship is between 9 over the square root of k squared minus 8 and 1 over k. So I graphed my function that I was interested in, the series that I was interested in blue, and then the one that I'm comparing it to in red. And clearly you can see that the graph in red, as we go out to 1,000, is going to be, the terms in that series is going to be smaller. So we would say that 1 over k is less than 9 over the square root of k squared minus 8. Because this series in red diverged, that means that our series is also going to diverge by the direct comparison test. So our conclusion would be that our series diverges by the direct comparison test when compared to the divergent p-series 1 over k. In order to do this test, you have to tell me what series you're comparing to, whether or not it converges or diverges, what the relationship is between the terms of the two series, and then your conclusion by the direct comparison test. All of that has to be included in your answer. You're not going to get some nice little 1 or 2 word answer here. All of this work together makes up your proof for this series, whether or not it converges or diverges. The next test we're going to look at is the limit comparison test. Now, the nice thing about the limit comparison test is you don't have to decide, well, that's not true. You do have to decide what you're going to compare to, but you don't have to look at the relationship between the two series, which one's bigger than which one or which one's smaller than which one. So that's why I like the limit comparison test a little bit better than the direct comparison test, because the limit comparison test says, suppose that you have an a sub n where the terms are greater than 0 and b sub n where the terms are greater than 0 for all n beyond some point where capital N is an integer. If the limit as n goes to infinity of the ratio of the two series is equal to some positive number, then the sum a sub n and b sub n both converge or both diverge. You don't have to look at the relationship between those two series. You just have to know what the one that you're comparing it to does. Typically, we want to just strip away the constants, and that's how we choose what we want to compare to. But you've got to know whether or not that series converges or diverges when you're choosing to compare it. If the limit as n approaches infinity of a sub n over b sub n is equal to 0, and the series that you're comparing it to converges, then your series will converge as well. If the limit of that ratio of the two numbers is equal to infinity and b sub n diverges, then we say that your series diverges as well. When we look at the limit comparison test that you were given here in our tests, This only tells us that the series will, remember this column is for convergence. This only tells us that if we get a limit that's equal to a finite number, a positive finite number, and our series converges, then our series we're wanting to compare to converges. And if we get equal to a positive finite number, then the series diverges. The two conditions that are missing from this test that I will allow you to add to your series formula sheet are these two conditions right here. You want to add this to your formula sheet. And I will let you use this on your test. So if you have your series sheet with you right now, go ahead and do that. I'll give you a minute. In example 3, I've got 3 different series here, and we wanted to determine the convergence when we're using the limit comparison test. The first thing we're going to do is we're going to decide what we want to compare these series to. So in part A, what do I want to compare? Well, I have a series n equals 1 to infinity, and if I strip away the constants, that square root is a power of 1/2, but we have an n cubed. N cubed raised to the 1/2 would be n over 3/2. And what does this series do? It's a convergent p-series because that power is bigger than 1. 3/2 is bigger than 1. In order to use the limit comparison test, then we're going to look at the limit as n approaches infinity of our series, 1 divided by the square root of n to the third plus 2, over the series we're comparing to, 1 over n raised to the 3/2 power. And that'll be the limit as n approaches infinity. To get rid of the complex fraction, we're going to flip and multiply by the fraction in the denominator. So that's going to simplify to n raised to the 3/2 power over the square root of n cubed plus 2. Hopefully what you notice here is that the degree of the numerator and the degree of the denominator are the same. They're both the 3/2 power. And we said that when that happens, this limit is going to be equal to the leading coefficient of the numerator over the leading coefficient of the denominator. So this limit is equal to 1. By the limit comparison test then, that means that both series will do the same thing. Since this one converged, I will conclude that my series converges as well. So our conclusion is that our series converges by the limit comparison test when compared to a convergent p-series. But you have to show what you compared it to and whether or not it converged and why before you can reach this conclusion. The limit comparison test is one of my favorite tests. On part B, we have this series. And we start by deciding what it is we want to compare it to. Our series right now is 2 to the n over 3 plus 4 to the n. If we strip away the constants, that's going to give us 2 to the n over 4 to the n. How can I rewrite that? Using the distributive property of exponents, we would say that that's equal to 2 over 4 to the n, which is 1/2 to the n. That means that we could compare this series in part B to the series n equals 1 to infinity of 1/2 raised to a power of n. And what do we know about this series? This is a convergent geometric series, and it converges because r is equal to 1/2 and 1/2 is less than 1. When we look back at the geometric series, we see that the conditions for convergence is that the absolute value of r is less than 1. So this is a convergent geometric series. In order to use the limit comparison test, we're going to look at the limit as n approaches infinity of the series we were given, that's 2 to the n over 3 plus 4 to the n, divided by, this is now going to be 1 over 2 to the n, because if I distribute that exponent, that's going to give me 1 to the n, which is 1, and 2 to the n in the denominator. Simplifying the complex fraction, then we're going to get the limit as n approaches infinity of 2 to the n divided by 3 plus 4 to the n times 2 to the n over 1. What is 2 to the n times 2 to the n? The exponents are the same. Can I rewrite that as 2 times 2 raised to a power of n? Well, that's just 4 to the n over 3 plus 4 to the n. And I see now that I needed to write that n more clearly as a power. So isn't the degree of the numerator the same as the degree of the denominator? That constant term as n goes out to infinity isn't going to matter a whole lot, and this is going to be equal to 1 as well. So we would conclude that our series converges by the limit comparison test when we compared it to a convergent geometric series. The reason it converged is because that limit was equal to a positive finite number. Remember, that's what this says. If the limit is equal to some positive, because it's greater than 0, finite number, then the series are either both going to converge or diverge. Since I compared it to a series that converges, that means that our series converges as well. On part C, we have the sum n equals 1 to infinity of 1 over 1 plus natural log n. If I stripped away the constants, what I would be looking at is this series. We have the series 1 over the natural log of n. I don't know anything about that series right now because it's not a p-series. It's not a geometric series. So I need to know something about that. Well, in order to know something about that, I'm going to compare it to the sum n equals 1 to infinity of 1 over n, because I know that 1 over n is a divergent p-series. Notice that 1 over the natural log of n is going to be greater than 1 over n. And if you're not sure about that, look at the graph of n and the natural log of n. So here's the graph of y equals n, and here's the graph of y equals the natural log of n. N is bigger than the natural log of n for all values of n. And what happens to a fraction when the denominator gets bigger? The value of the fraction gets smaller. So I feel confident in saying that this inequality holds true. Because I found a smaller series that diverges, that means that the sum of the series 1 over the natural log of n is going to diverge by the direct comparison test. So now I'm ready to look at my limit comparison test because I've shown that the terms of this series will diverge as n goes to infinity because I proved that this diverged by comparing it to a divergent p-series. So now I'm going to look at the limit of the terms of this series over the terms of this series. And that's going to give us the limit as n approaches infinity of the natural log of n divided by 1 plus the natural log of n. As n goes to infinity, this is in an indeterminate form. So that means then that I could set this equal to the limit as n approaches infinity of the derivative of the numerator over the derivative of the denominator, and that's going to be equal to 1. Because that limit is equal to a positive finite number, we can conclude that our series is going to diverge by the limit comparison test when compared with the divergent series 1 over the natural log of n. Now just for giggles, what if I didn't want to take this intermediate step? Could I have just looked at this series and said, well, these terms, the denominator is going to be less than n, why not compare it to 1 over n? What would have happened if we did that? Let's investigate. So this is going to be an alternate proof. If we look at the limit as n approaches infinity of 1 over 1 plus the natural log of n divided by 1 over n, that's going to give us the limit as n approaches infinity of n divided by 1 plus the natural log of n. This is an indeterminate form, so I end up with infinity over infinity, and that means that this would be equal to the limit as n approaches infinity of the derivative of the numerator over the derivative of the denominator, and that's going to be the limit as n approaches infinity of n, and that's equal to infinity. And we had that condition on the limit comparison test that said that if you get infinity for your limit and the series you compared to diverges, then your series will also diverge. I could have used either one of those, but these bottom two examples on this limit, it's rare that we use them, so typically I don't remember them. And I knew that this was going to happen whenever I looked at the limit of the ratio of those two things. So that's why I chose to use this intermediate step here. And it's a good idea to show you how to do this because sometimes that happens. If you can't tell directly that what you want to compare to is going to converge or diverge, you have to use another test to show that that series either converges or diverges. So that's a skill that you needed to see because it's a skill that you may have to use. But notice we got the same conclusion. Our series is going to diverge by the limit comparison test. The path you take to get to the answer does not change the answer. And we have one more example to look at here. We want to determine the convergence using the limit comparison test for this series. So notice that the natural log of x is less than x for all values of x. And I showed you that with a graph. Here's a graph of y equals x. and this is a graph of y equals the natural log of x, we feel safe in saying that the natural log of x is less than x. If I were to square both of these sides, this inequality would hold true. The natural log of x squared is also going to be less than x squared. Now, I mentioned that to help us see what it is we want to compare this to. You got to have some idea before you begin what this is going to do. So I know that the natural log of x is going to be less than x. So this is going to be some power that's going to be less than 2, which means that when I divide a power that's slightly less than 2 by n to the third, this power in the denominator is going to be slightly larger than 1. If you have the natural log of n squared divided by n cubed, then if I look at x squared divided by x cubed, this value is going to be less than this value, isn't it? Which means that since this power, I could write this as a power that's going to be less than 2. That means that this power, when I reduce these powers here, would be something that's slightly bigger than 1. So I'm going to pick a series of 1 over n raised to the 1.05 because that power right there is slightly more than 1. Because this power would be slightly less than x squared, I'm going to pick a number that's just really, really close to that. I'm going to compare it to this series. I need to look at the relationship between these two. Actually, no, I don't. I don't need to look at the relationship between these two series. So I'm going to use this. This series is a convergent p-series. And then let's try using the limit comparison test. So we're going to look at the limit as n approaches infinity of the natural log of n squared divided by n cubed divided by 1 over n raised to the 1.05 power. And we can write that as the limit as n approaches infinity of n raised to the 1.05 times the natural log of n squared over n cubed. Here, when we're dividing with a common base, we can subtract the exponents, and that's going to leave us the limit as n approaches infinity of the natural log of n squared over n raised to the 3 minus 1.05 is going to be 1.95. And this is an indeterminate form, infinity over infinity. That means that we can apply L'Hopital's rule, and that would give us the limit as n approaches infinity of, we take the derivative of the numerator, and that's going to give us 2 times the natural log of n to the first times 1 over n divided by 1.95 n raised to the 0.95. Let's simplify this. There I can kick this term into the denominator, and that's going to give me the limit as n approaches infinity of 2 over 1.95 times, I have the natural log of n in the numerator, and then in the denominator I'm going to have n raised to the 1.95 because this n got moved down here, and when you multiply with the common base you add the exponents, so that's going to be n to the first times n to the 0.95 is n to the 1.95. This is still an indeterminate form. It's infinity over infinity, which means that I can apply L'Hopital's rule again, and this is going to be equal to the limit as n approaches infinity of the derivative of the numerator over the derivative of the denominator, and I don't know why I switched to an x all of a sudden, but that's going to be 2 over n times 1.95 squared n to the 0.95. That term can be moved into the denominator, and that would give us the limit as n approaches infinity of 2 over 1.95 squared n raised to the 1.95. Now as I let n go to infinity, this gives me 2 over infinity, and 2 over infinity is 0. I compared our series to a series that I knew converged. When we look at the limit comparison test, we said that if we get a limit that's equal to 0 and the series we're comparing it to converges, then our series converges. So because we compared to a series that converged and our limit was equal to 0, our conclusion then would be that our series A sub n converges by the limit comparison test. And I don't mind you using these abbreviations for limit comparison test. We don't want to write out all those words, right? Well, this wraps up section 10.4.